Hello, my name is Gary Mandyam. I work at Qualcomm Incorporated, based in San Diego, California, but I'm also the chair of the FIDO Alliance's IoT Working Group. And today, I would like to talk to you the IoT Security Foundation's annual conference about secure onboarding for IoT devices, particularly a focus on the FIDO approach. So IoT devices provide much promise in home and industrial automation and many other applications, smart infrastructure, smart cities, and several other applications. Data communications from these devices provide a lot of promise, but also introduce a new threat vector. Many of these devices are low cost, and particularly manufacturers would like to achieve the same cost targets as they would today with their with current commoditized products. I mentioned light bulbs and low-cost sensors. As a result of that, there's a lot of trade-offs between how much a manufacturer can invest in technology, particularly to protect the device, versus the actual sales price of the device. Many parties are involved in the IoT supply chain. Today, you see semiconductor vendors playing a role of prominence. Also, the actual finished product manufacturers, and finally, the end users. You may also see intermediaries who are also involved in the IoT supply chain. An onboarding of device owner is very tough to get right. Establishing a relationship between the owner and the device is not something that's is not a problem that's universally solved today. So what does onboarding entail? I have outlined three primary steps. The OEM first manufactures the device and ships it. The end user purchases the device, installs it in the expected place of operation, and powers it up for the first time and can actually establish ownership. Once ownership is established, the onboarding process is complete. Zero-touch onboarding is a goal for most manufacturers. That involves having minimal intervention on behalf of the user in order to establish ownership. So one particularly common approach could entail downloading an application on a personal device like a smartphone or a tablet, establishing a connection with the cloud service, while also using the personal device to establish a connection to the IoT device. Once that bridge is created through the personal device between the IoT device and the cloud service can actually go ahead and complete the ownership transfer to the intended end user. So some of the challenges with onboarding, there's a wide variety of equipment, not just hardware, but also software too, particularly operating systems. You see this a lot in the IoT ecosystem. Also, another thing you see a lot in the IoT ecosystem is many devices are headless. They don't have sophisticated user interfaces that would allow an end user to interact with them and manage them. You also find different types of connectivity that are supported in the IoT device. It's not just a wireless versus wired. It could also be different types of wireless technologies, such as NFC, near-field communications, Bluetooth, wireless LAN, etc. Also, another thing to bear in mind is manual installation adds a lot of time and essentially money, and it can affect the return on investment, particularly when you look at enterprise applications where many of the persons involved in procurement and deployment have to weigh against the benefits of having connected devices versus the cost of installation. And then finally, many times you need trusted and skilled installers in order to make the whole onboarding process smooth and complete. So what could go wrong in onboarding? Well, I'll go back to the onboarding app example that I mentioned a couple of slides ago, where the app is actually used to intermediate between the IoT device and the cloud service. A cloned or compromised device can be used as a potential attack vector on the end user. A cloned device could lead the user into certain types of attacks from giving up personal information to potentially more disastrous types of attacks where financial information is disclosed. And it becomes really problematic if neither the app nor the cloud service picks up on the cloned device. Communications can be compromised if the communications aren't secure between the IoT device and the app, or the app and the cloud service. Then third parties could potentially eavesdrop, or worse yet, intercept and modify communications between the three participants in the communications link. Then finally, ownership may never transfer. This has its own challenges when the end user never establishes an ownership relationship with the device. Then there could be another party that's in the position to manage the device through its life cycle. So now I'll talk a little bit about how the FIDO Alliance went about developing a standard to address secure onboarding. The Fast Identity Online Alliance is a standards and certification body focused on primarily passwordless authentication. And there are several standards that actually enable such kinds of authentication, including biometrics. There's also associated security and functional certification programs. Recent standards efforts have been focused on the IoT space, and particularly the area of secure onboarding. The IoT working group actually started with a base set of use cases and requirements by a variety of member companies, some coming from cloud service providers, some coming from the original equipment manufacturer community, and some coming from the semiconductor industry. The first specification was released in August of 2020, and there's a hyperlink provided in the presentation. So what do we see as far as the use cases are concerned that were contributed to the working group? They actually fell into three broad categories. Category 1, which is deployment, Category 2, which is binding, Category 3, which is enablement. The deployment use case is primarily focused on the whole area of secure onboarding, starting with the device from manufacturer through supply chain to the end user premise. Category 2 is binding. This is sometimes occurs a little later in the device life cycle. This is actually where ownership of a device can be transferred temporarily or through some sort of bounded agreement to a different owner while the conditions of the bound are met. Sometimes it could be time-based, such as a rental agreement. It could be geolocation-based as well. For instance, an end user has access to a device when he's in a particular room or a particular building. Finally, Category 3 is enablement. This is after onboarding has taken place. A device can have its features locked or unlocked based on hardware activation. So this could be related to upsell or downsell of hardware-bound features. For example, could be enablement of new wireless capabilities in a device that may not have been enabled at the point of sale. Note that many of the we also concluded that many of the solutions that could be used to address Category 1 could also potentially address Categories 2 and 3. Now, this is another view of the use case categorization in the FIDO IoT working group. As you can see, Category 1, which is by far most of the use cases contributed by member companies, has several aspects to it. I'll start at the top with the difference between a trusted and an untrusted installer. So what is meant by that? Well, sometimes the installer could be trusted in that the end user of the device is the same person who is actually installing the device. You may see this a lot in home automation. For instance, I may be installing a connected thermostat in my home. So therefore, there's a trust relationship between me as an installer and me as an owner, one and the same person. An untrusted installer you may see more in enterprise environments where a maintenance crew possibly would be installing connected light bulbs in a conference room, but the actual end users of those connected light bulbs could be the enterprise itself. The maintenance crew may have just be on a contract with the enterprise. Common late binding solution. What does that mean? That means that ownership can be bound to an end user after installation and the first power up. Until that time, ownership may belong with the manufacturer of the device. So the smooth transfer between manufacturer to the end user will actually allow for a common late binding solution across a wide variety of IoT products. Disabling or resell, that could be sometimes we also refer to that as a factory reset case, where essentially a device can be returned back to an original state post-manufacture where onboarded again. And then enabling and disabling of certain hardware and software features upon ownership transfer. The second category, as I mentioned, was bound ownership. And then finally, the third category on the right, as I mentioned before, enabling or disabling hardware and software features after ownership has been established. All of these use cases are meant to be addressed on different network scenarios. You could have open networks, such as the open internet, closed or private networks, or just a hybrid model where parts of the network deployment are private and parts are not. And also, the network could be the network owner could be different from the end user. So this is a depiction of the FIDO IoT system architecture. As can be seen, there are three primary endpoints in the system architecture. There's the device to be onboarded, then there's a rendezvous service and an onboard owner. Finally, the communication between these endpoints can be intermediated through gateways or personal devices. So I mentioned from the primary actor perspective, I mentioned the IoT device to be onboarded. What are some of the other actors? The actual device manufacturer, the gateways, if they're applicable. This would bridge connectivity between the device and the owner. I mentioned a rendezvous server. What is that? Upon first power up, the device contacts this actor to obtain information on how it can contact the device owner. So this allows the device owner to only be contacted by devices that are suitable for onboarding. And then finally, the device owner, it will prove that ownership to the actual device and then manage the device during its life cycle. So there are four primary protocols that actually make up this process. Device initialization is a protocol that executes in the manufacturer's factory, and that involves the provisioning of the IoT device with certain credentials and other information required to actually initiate and complete a secure onboarding process. Then there are three stages to the transfer of ownership, reflected in three different transfer ownership protocols: TO0, TO1, and TO2. TO0 is where a device owner contacts the rendezvous server and seeds it with information on devices to be onboarded. This would usually take the form of, at a minimum, a unique identifier, what we call a GUID, a global unique identifier, that the rendezvous server can use to actually determine if an authentic device is contacting it. And then it would also provide additional information to the rendezvous server on how to contact the device owner so that this information can be provided to authentic devices. TO1 is where the device contacts a rendezvous server upon initial power up, for instance, after initial sale or after a factory reset. And this is where the device actually can prove to the rendezvous server that it is an authentic device, usually by presentation of, at a minimum, the GUID, along with any other information needed to validate itself in a secure manner. Then after TL1 completes, the device to be onboarded will have information on how to contact the device owner, and it will contact the device owner. As part of the TO2 exchange, there will be a mutual authentication, and then the device owner will actually take over management of the device for its life cycle. Some of the critical onboarding authentication credentials that are required for the FIDO secure onboarding process are the device credential. It's a manufacturer provisioned key pair that is used to identify the device specifically for onboarding. It's not meant to be used by the device through its entire operation. The device ownership key pair. An IoT device is seeded with an initial key pair, and that ownership key pair can be replaced multiple times during its life cycle. Then there's also related unique information. There's the ownership voucher, where the manufacturer creates a voucher based on the initial ownership key pair, and that can be actually presented to the device to establish ownership by a device owner. And then I mentioned the device globally unique ID. So what role does attestation play in onboarding? Attestation, if we go by one particular definition that I provide here, it describes the process by which software executing on a device provides an assertion to a relying party about the integrity of its platform. So what is a relying party? It's any service provider that actually consumes the attestation produced by a device, usually as part of some transaction, could be part of onboarding. And in the case of IoT devices, and in case of FIDO onboarding, both the rendezvous server and device owner consume the attestation produced by the device. The attestation can be based on several criteria, including an assessment of the operating system kernel as an example, an enumeration of all third-party applications that are installed on the device. You see this much more, for instance, in personal devices such as tablets or smartphones, where end users can install applications from different app stores. But you do see this also in the IoT device space. Also, if any suspicious events have occurred, such as protected memory access, that can be logged and provided in the form of an attestation. Attestation data is usually formed by combining indications of all these different criteria into a payload, and that payload usually takes the form of a compact data structure that can be sent to a relying party. It should be cryptographically verifiable. That would mean that it can be signed, and it can be signed by the attesting device, and that signature can be verified by the relying party. It can also be encrypted too, because many attestation statements contain a lot of unique information that could be used to violate the privacy of an end user or through the associated device, or can be used to potentially compromise the device if it's obtained by the wrong, if it falls into the wrong hands. So attestation and onboarding is actually applicable to two of the protocol stages I mentioned before, TO1 and TO2. TO1 is where the device establishes its authenticity to the rendezvous server, and TO2 is where the device attests to the device owner. You could also see mutual attestation occur in those flows, even though it's not defined in the FIDO specification, if it makes sense, depending on the deployment. Attestation information often differs between TO1 and TO2. The reason for this is that the rendezvous server will likely not need as much information about the device, and particularly the device's security state, as a device owner. The rendezvous server only needs the minimum amount of information necessary to establish that the device is authentic before it directs it to the device owner. As I mentioned, other interactions where attestation can be required. TO0, rendezvous server and device owner can attest to each other as part of the device owner seeding the rendezvous server with the necessary information for onboarding. And then TO1 and TO2, where the rendezvous server and the device owner establish their security state to the device to be onboarded. So the device security architecture also plays a role in onboarding. And this is actually relevant to a lot of the work that the IoT Security Foundation has done in developing security requirements that can be used in a security certification program. Ideally, critical device credentials should be stored in a secure part of the device. What is the critical information associated with device credentials? Private keys and any crypto operations that are performed using those private keys would ideally be protected in a secure environment and reduce their vulnerability to attacks. As I mentioned at the beginning of the talk, IoT device manufacturers are often left with the quandary, though. How much are they willing to invest in protection against attacks by protecting this key material in a secure environment versus versus their target price points for the device? So as a result of that, the device owners should adjust their security policy based on the security characteristics, particularly the hardware security characteristics of the device. If the device owner knows that credentials aren't being protected in a secure environment on the device, then the device owner should actually take that into account. Maybe have, for instance, more regular audits of the device, and those audits could take place not just in the form of over-the-air communications, but also physical access and inspection of the device. So in addition to the FIDO standardization, there's also a new effort in the Linux Foundation EDGE project to develop an open source implementation of the onboarding specification. And this is now just started. This work is at its very beginning. And as you can see with the hyperlink provided on this slide, the code is open source. So independent parties can actually go ahead and access the code, experiment with it, provide feedback, more importantly, to the foundation, so that the code can be improved. We are expecting a production quality release of the LF Edge code by sometime later this year, but this also depends on which directions the specification takes. Because we just released our initial version, as I mentioned, in August of 2020. There's still a lot of work to do. It's a good time to get involved. The first implementation of the standard has come out, but we are looking for implementer feedback. We are planning to roll out from the FIDO Alliance an interoperability program and a security certification program. There are some additional features to be defined. How the FIDO onboarding works in private networks. Currently, the specification is fully specified for internet-connected devices, but as I mentioned before, many IoT devices do not have internet connectivity. The role of the trusted installer, how an end user, for instance, uses a application on their own personal device to complete the whole onboarding process. And I mentioned the Category 2 and Category 3 use cases. We are still interested in looking into and solving those particular problems associated with that. We are developing reference architectures, end-to-end system architectures. FIDO has a rich history of doing that to help deployers out. And then also regulatory outreach. As we're seeing more and more, we are seeing many governments and other standards organizations look into regulations and regulations for IoT devices. And it is a bit of a challenging space, given that we're seeing many regional efforts come up in this space, and it may not always be easy to develop a standard that can comply with all the requirements around the world, but we're certainly going to try. So I'll summarize. Solving the challenge of secure device onboarding with minimal user intervention, the zero-touch goal, is the key to the growth of IoT. It's needed to, and the primary goal is to make sure that the device owner is clearly established and has exclusive control over device management during the entire life cycle, from when they first power up to when the device reaches the end of its operation, for instance, during as a result of a factory reset. The FIDO Alliance and its members are making fast progress, and there is an open source implementation underway, but it is a good time to get involved. And we invite all interested companies to review the draft, specification, and evaluate the software today. I'd like to thank the organizers of the IoT Security Foundation's annual conference for inviting me to give this talk, and I'm open to questions now. Thank you.